If you've studied calculus, you know all about the exponential function, the log, the sine, and the cosine function. For sure, these are four of the most important functions in mathematics. But what you might not know is we can start from one equation and define all of these functions. Y prime equals y. The choice of initial condition for y just sets the scale, so we might as well assume y of 0 equals 1. We can call the solution of this differential equation y equals EXP of x, a name which should be familiar. But for now, let's just pretend we know nothing about this function. We may as well also find the equation for the inverse of EXP and call it the natural logarithm with the symbol Ln. Because EXP and Ln are inverse functions, they satisfy the relation EXP of Ln of x equals x. We can take the derivative of both sides using the chain rule and the differential equation for EXP. We get EXP of Ln of x times the derivative of Ln of x equals 1, which simplifies to the derivative of Ln of x equals 1 over x. This is a most welcome formula in a calculus course because we already know that the derivative of x to the n is equal to n times x to the n minus 1. And when n equals 0, we're taking the derivative of a constant term, which gives us 0. So we never get the derivative equal to 1 over x. Since EXP of 0 equals 1, we know that Ln of 1 equals 0. So we can integrate both sides of the differential equation for Ln of x to get Ln of x equals the integral from 1 to x of dx divided by x. This integral is one way of defining the natural logarithm. We can easily plot the EXP and Ln functions either by hand or using a software such as MATLAB. We start at x equals 0, where y is 1, and draw a tangent line of slope 1. We can march the solution forward in x, keeping the slope of the tangent line equal to the value of y. We see that the function increases rapidly. We can also march backward in x. The slope of the tangent line then decreases as y decreases, and the function eventually asymptotes to the negative x-axis. Once we have the EXP function, we can easily plot its inverse, the Ln function. We simply reflect the EXP function across the line y equals x. We define the EXP function as a solution of a differential equation, but we can also define it as a power series. Recall the Taylor series for the function y equals y of x. If y is the EXP function, then y of 0 equals 1. And since y prime equals y, all the derivatives of y at 0 equal 1. So EXP of x has this simple form. Now if we multiply the Taylor series for EXP of x times EXP of y and then collect terms, it's pretty easy to show that EXP of x times EXP of y is equal to EXP of x plus y. This identity is the one for exponents, which is why we call EXP the exponential function. It's common to write EXP of x equals e to the x, where e is a special number called Euler's number. Euler is a famous mathematician, but apparently Jacob Bernoulli first discovered e while studying compound interest. The choice of the letter e by Euler might mean exponent, but of course e is also the first letter of his name. The value of e can be found from EXP of 1, which is this infinite series. E is an irrational number, so we can't write down all of its digits. But here is a table showing the sum of the first n terms in its series. We can see the value 2.7182818 emerging. Once we have EXP in hand, we can define the cosine and the sine by making use of the imaginary number I. We can write the Taylor series for y equals e to the ix and get this power series. And we know that I to the 0 power equals 1, I to the first power equals I squared equals minus 1, I cubed equals minus I, and then I to I fourth is equal to 1 again, and the cycle repeats. So the Taylor series for e to the ix simplifies to this, which we can rewrite by collecting the real and the imaginary parts. So now we can define two real functions, which we'll call cosine and sine, pretending we don't yet know what those are. So cosine x equals the real part of e to the ix, and sine x equals the imaginary part of e to the ix. And the definitions of cosine x and sine x are given by these power series. The relationship between the exponential function and the cosine and sine functions is then usually written as e to the ix equals cosine x plus I sine x. This famous formula is known as Euler's formula. The physicist Richard Feynman called Euler's formula the most remarkable formula in mathematics. We can determine the differential equations satisfied by these new functions, cosine and sine. We know that the differential equation for EXP of Ix is given by y prime equals Iy, with y of 0 equals 1. This is a complex differential equation that we can write as two real equations. Let y of x equals u of x plus I v of x, where u of x and v of x are two real functions. The complex differential equation then becomes u prime plus I v prime equals I times u plus I v. This separates into two real equations, u prime equals minus v and v prime equals u. The initial conditions are u of 0 equals 1 and v of 0 equals 0. We can do a little bit of analysis. If we multiply the first equation by u and the second equation by v and add these two equations, the right-hand sides cancel. We then get u times u prime plus v times v prime equals 0. And using the product rule from calculus, this becomes 1/2 d dx u squared plus v squared equals 0. So we see that u squared plus v squared is a constant. Since we know that u equals 1 at 0 and v equals 0 at 0, then u squared plus v squared must be equal to 1. This is just the familiar equation cosine squared x plus sine squared x equals 1. Now let's plot the solutions for cosine and sine. We can draw two plots, the top plot for u equals cosine x and the bottom plot for v equals sine x. Cosine x starts at 1 and sine x starts at 0, and the derivative of cosine x is negative sine x, and the derivative of sine x is cosine x. We can draw the tangent lines and march the solutions forward. As the solution for a sine rises from 0, the solution for a cosine falls from 1. We can continue marching the solutions forward until cosine x equals 0. We will call the x value of this 0 pi divided by 2. In other words, we're defining a new number pi such that it's twice the first positive 0 of the cosine function. Since cosine pi over 2 equals 0, we must have sine pi over 2 equals 1. We now have a plot of cosine and sine from 0 to pi over 2. And in fact, that's all we need. But we have to first derive the addition identities for sine and cosine. We can write e to the I x plus y equals e to the I x times e to the I y. Then applying Euler's formula, we have cosine x plus y plus I sine of x plus y equals cosine x plus I sine x times cosine y plus I sine y. Multiplying out the right-hand side and taking the real and imaginary part of this equation, we obtain the addition formulas. For y equals pi over 2, we obtain cosine x plus pi over 2 equals negative sine x, and sine x plus pi over 2 equals cosine x. So we can extend our graphs for cosine and sine from pi over 2 to pi by just attaching graphs for negative sine and cosine to the ones we've already computed. And we can continue extending the graphs of cosine and sine out to x equals 2 pi, after which the graphs become periodic. Now, without going into detail, we can use our discovered properties of sine and cosine to show that the circumference of a circle is 2 pi times the radius, and the area of a circle is pi times the radius squared. My personal favorite identity in mathematics is the Euler identity, which gives us a relationship between pi and e. If we apply Euler's formula and use cosine pi equals -1 and sine pi equals 0, we can obtain the identity e to the I pi plus 1 equals 0. This is an identity between the 5 most important numbers in mathematics: 0, the addition identity; 1, the multiplication identity; I, the unit imaginary number; pi, the most important number in geometry and trigonometry; and e, the most important number in calculus. Euler's identity gives us a relationship between these 5 numbers using only 1 addition, 1 multiplication, and 1 exponentiation. When the sine and cosine functions first appear in a differential equations course, they are solutions of second-order differential equations. We can find this second-order equation from our system of first-order equations. On the one hand, if we differentiate the u prime equation and substitute in v prime equals u, we obtain u double prime plus u equals 0. Together with the initial conditions u of 0 equals 1 and u prime of 0 equals 0, we find u is equal to cosine x. On the other hand, if we differentiate the v prime equation and substitute in u prime equals negative v, we get v double prime plus v equals 0. If we use the initial conditions v of 0 equals 0 and v prime of 0 equals 1, we find v is equal to sine x. So starting with the simple differential equation y prime equals y, we've defined the exponential function, the natural logarithm, and the sine and cosine functions. We've also defined the 2 very important numbers pi and e. I'm Jeff Chasnov. As always, thanks for watching.